So I think we'll begin the presentation. So thank you so much everyone for joining this webinar. Uh, it's one of our series of webinars that we've been conducting during this lockdown period for our partners and our customers so that they can learn about Wi-Fi, how all these technologies work and so on. So I think this is a continuation of this training program. We have been getting an overwhelming response for all these programs. So we really would like to thank all of you for the support and the encouragement that you have shown. And we sincerely hope that whatever we share, the knowledge and our experiences will be beneficial to all our partners and our customers. With that, I think let's begin with the presentation. I think everyone should be able to see my PowerPoint. I think we have a very exciting topic today. Basically, we are going to discuss a lot of things about uh, Wi-Fi and the basics of Wi-Fi. So let's get started. So I presume everyone is on my screen. So let's. The topic of today's discussion will be Wi-Fi basics. So before that, I think many of you have attended our previous webinar that covered primarily a lot of RF related topics, RF basics. We are still hearing some background noise. Just a minute. So our previous topic was related to RF basics, where we discuss about how radio frequency operates, what are some of the challenges of radio frequency, how it penetrates and how it propagates through the air. I'm sure a lot of you would have got insights into this amazing technology that's the fundamentals or the basics of how Wi-Fi works. So again, this time we are having another interesting topic about the details of Wi-Fi. So just like our previous presentations, I will just encourage people that this is going to be very technical topic. A lot of networking related fundamentals will be discussed. So I would encourage people to please first of all mute their microphones. Don't draw any random things on the white or using the whiteboard or this thing. So please refrain from doing that. And lastly, if anyone is not very technical and may not be interested in the topic, we would encourage them to drop off, because we have overwhelming response. We have more than 100 participants who are joining in, and the people are just waiting for in the outside to join the conference. So this is again going to be another very technical topic, and you will learn a lot of things about how Wi-Fi works and what are some of the really interesting aspects of Wi-Fi. So let's go forward, as in let's understand and delve deeper into what is the basics of Wi-Fi technology. So before we get into Wi-Fi, I think all of us needs to understand the concept of ISM bands. As many of you know that Wi-Fi works in a free spectrum, or a spectrum for which you don't have to pay any government licenses. Unlike your cellular technologies or your any other, like you use radar or you use any other radio technologies, you're like, for example, you want to broadcast a radio signal, you want to broadcast like a radio station, you have to pay licenses to the government to operate in that spectrum. But Wi-Fi was designed for being right from the start, it was designed to be a free spectrum. The main basics of it, obviously it originated in the United States. At that time, while the spectrums were getting allocated, the US government decided that for research and development and for medical institutions, there should be some spectrum that they should allocate and keep it free so that people can use it freely, and it will spur innovation. And that's exactly what has happened, as in the spectrum was kept free. So any person who had the knowledge of RF and Wi-Fi, RF technology, was able to explore. And that's what the universities and the research lab in the US did. And then they came up with this Wi-Fi protocol. Similar to Wi-Fi, there were many other protocols that were built. We'll not get into that because the main topic of our discussion is related to Wi-Fi. But nonetheless, I think that really in 70s and 80s, when this was enabled, it really spurred a lot of innovation. Um, Please mute your microphones. Again, I'm encouraging everyone, and don't unmute it, although I'm giving that option because people would like to ask questions. So I'm allowing the participants to unmute, but please mute yourself. There are three primarily ISM bands. ISM stands for Industrial, Scientific, and Medical bands. These have been basically designed. These ISM bands are specially kept aside for these three primarily applications. Although now I think that band now does everything. As in, Wi-Fi is being used for everything now, right from recreation to people have built large businesses in these bands. Anyway, so there are three bands. There is a 900 megahertz band, there's a 2.4 gigahertz band, and there's a 5 gigahertz band. And all of you know, I think many of you may be surprised that there is already a 900 megahertz band. Although we don't see anything operating, or no appliances or devices are there which broadcast in 900 megahertz. But nonetheless, this actually is a band, but it is a very small band. As you can see, 26 megahertz band, and there is not much you can do in that band. As in, although the main reason why this band is there, or its main use could be, it sits in the lower frequency spectrum. It has really very good penetration power. So it can go through leaves and vegetation, and can people ISPs actually do use it for point-to-point links, because those links have to go through a lot of vegetation or trees and so on. And so there, I think ISM 900 band is used even today. Now, you may ask in India whether it is true or not. We'll have to check Indian government, because every country has a different regulations of which ISM bands they will allow. So not necessarily if it is allowed in the US, it will be allowed in other countries. Now, the next band which everyone knows is the 2.4 gigahertz band. I think all of you are quite aware of this band. This is the band that we most, and is most frequently abused band as well. Um, so this band offers you 100 megahertz frequency. Basically, there's a spectrum that is allocated of 100 megahertz. So because there are 100 megahertz, uh, there is a wider channel. So that's why it's been very successful in a sense, and has been used has been used worldwide. Now, this band frequency goes from 2.4 gigahertz all the way to 2.5 gigahertz. And this, we are talking in US context. Again, now in India, again, almost the same band is supported. I think we have a 100 megahertz band in India as well. Now you may be wondering that we always look at a 2.4 gigahertz band always in terms of Wi-Fi technology, but that's not true. As in, it's actually 2.4 gigahertz is used for a lot of applications. In fact, and your Bluetooth applications also use a 2.4 gigahertz band. So it's not that 2.4 is exclusively reserved only for Wi-Fi. There are other technologies. In fact, your microwave oven in your kitchen will be also using the 2.4 gigahertz band. In all, there are 11 or 13 bands available, and I'll talk about what those bands mean. I mean, the 2.4 gigahertz is the frequency range. So the Wi-Fi, the IETF, which is the task force which is responsible for under which IEEE lies, they are responsible for creating the Wi-Fi specifications. They divided into separate bands. So depending upon which country you are in, you will be allocated either 11 or 13 bands. I think in India, 11 bands are allowed. Then we'll go to the 5 gigahertz band. Now 5 gigahertz is a much band. The reason being that it was a part of like there are a lot of pressure on the government, especially in US, a body called FCC, which is regulating or is controlling all the frequencies in the US. So there were all the standards UNII1, UNII2A, and so on. I will not get into the tech details of it, but you have to understand that each of these provides you a set of bands. Now, earlier, this was when we are talking about 802.11a standard, there was only one band, which was a 5.8 gigahertz band, which was available earlier. But there was a lot of pressure built on the governments, and then they opened up more bands. So now, because there is range of frequencies available in 5 gigahertz band, we are in the 5 to 6 gigahertz band. That's why we call it a 5 gigahertz band. As many of you might know that recently FCC has recently even allowed 6 gigahertz band for Wi-Fi. So this was one of the big news that came out of US last month, when they allowed the 6 megahertz band, gigahertz band. So that's going to be that will revolutionize the Wi-Fi industry, because all of a sudden a very wide spectrum has become available. And there were some, whatever their shortcomings of the 2.4 gigahertz were covered in the 5 gigahertz band as well. So let's go forward and see a little bit more deeper into this. So let's understand the 2.4 gigahertz band. I'm sure many of you would have seen this images, right? What we have drawn here is the frequencies on this line from 2.4 gigahertz all the way to 2.5 gigahertz. And you can see that these are there are like these umbrellas that are created on each of those bands, right? So the idea that here is that there are 11 or 13 bands, depending upon how you're looking at it. But you can see that there is a lot of overlap that is happening between these bands. So 1, 2, 3, 4 actually, and 5 are actually overlapping with the signal from 1, as in if 2, 3, 4, 5 are overlapping with the signal from 1. So that essentially makes all these other bands useless if you are broadcasting in channel 1. It's called interference. It's called the channel interference, and that is what is happening. So effectively, what you get is the picture on the right hand side. So the distance between two bands needs to be 25 megahertz for them to not overlap, and that's how the Wi-Fi protocol or the Wi-Fi technology has been designed. So because each of these bands had the difference between 1 and 2 is only 5 megahertz. So if you have two channel access points operating in one is operating in one and other is operating in two, you are definitely going to have a lot of interference, as you can see here. So I think many of you would be aware that you need to operate in this kind of band structure, right? And the reason being because of this channel interference. Now let's understand the 5 gigahertz band. So sorry, let me just, can I get rid of this? So let's understand the 5 gigahertz band. Now what happened is, because they got a lot of time to design the 5 gigahertz band, they realized that there are some shortcomings. One of the shortcomings of 2.4 gigahertz, if you go back to the previous slide, is that the channel assignment begins right at 2.4 gigahertz, which is right here. So if there is any other license frequency operating before 2.4 gigahertz, it will automatically interfere, or this particular band will interfere into the license frequency. So what 5 gigahertz it did is what they called as the guard band, or if you notice here, this is made to be 30 megahertz. So on both sides, they kept 30 megahertz free. And this automatically created a guard so that the Wi-Fi signal would not overlap with the other signals or other license signals used for other applications. Now, on the picture on the right hand side will show you how many different channels are available in 5 gigahertz. So there are multiple range of frequencies which are allocated in 5 gigahertz. So there's a 5.15 gigahertz all the way to 5.35 gigahertz. And I'm given the numbers. These are, I think, the standards that are called UNII1, UNII2A, and so on. So for more interest, if those who are interested and can go and read about that. But this is basically a bigger length. So you can see this is almost more than 200 megahertz band is available here, right? So here you have um, 20 megahertz difference. If you have a channel, if you are creating a band or a channel which is having a 20 megahertz length, so you can create lot many channels here, or lot many channels are available for you, right? So this is why people, when they talk about the 5 gigahertz band is more, gives you more bandwidth compared to 2.4 gigahertz. This is the reason why. Secondly, you can see that another channel which is available, which is from 5.5 all the way to 5.72 gigahertz. So again, there are, whatever you see here are basically the channels which are available in this band. Lastly, from 5.725 to 5.825. Okay, these are the bands which are available. Now it's get a little tricky later on. I will get into that the details, because soon after opening up this band, the US government realized that a lot of weather radar, like in US there are a lot of weather stations, and they allocate for weather radars, they allocate certain bands here, so they get overlapped. So some of these bands actually get overlapped with that radar bands as well. So they have created a unique combination that if you find a radar signal nearby, then you should not be operating in that. Please, someone, I will. Please don't draw anything on the. How can I stop this? This is bad. Please don't do anything on the slides. Who is drawing this on the slides? Guys, this is not professional at all. Please don't. Please stop doing that. If you are not interested, get out of the room, please. So the this is the this, as you can see, that these bands are there. So what happens is, because you are having a lot more spectrum available, you have you can do a lot more throughput through that. Okay. Now there is also, because you have bigger bands available, there is a unique concept which is called channel bonding that you can enable in 5 gigahertz. Although it can also be done in 2.4 gigahertz, but it is really effective in 5 gigahertz, because here you can get a lot more channels, 40 megahertz channels. So basically you aggregate 20 megahertz channels and you get 40 megahertz channels, and because you get double the bandwidth, you basically are increasing your throughput. And we'll see that how, by doing this channel bonding, you are effectively the bandwidth, and what are the pros and cons of doing that. So just for everyone's this thing, if you have any questions, feel free to type in the chat box. I will review those questions at the end of the presentation, and our technical team is also there on this call, so they may also answer some of these questions while the presentation is going on. So if you have any questions, feel free to use the chat box to raise your questions. We will review them at the end of the presentation. Now, I was telling you about channel bonding, and I'm sure many of you may not be aware of this concept as well. So I'll try to explain it in more detail here. So on the top, you are seeing the 5 gigahertz bands that we saw earlier, right from 5.15 to 5.35 and 5.47 to 5.725, so on, right? Now these, on the top, what we have drawn are basically the channels, as in 36, 40, 44, 48, and so on. These are the channels in the 5 gigahertz band. Similarly, on the right hand side, and the orange colors are the ones which have been proposed to the FCC. If they get approved, then it will add more bandwidth to the 5 gigahertz. So that's why they are in orange. Um, so what you can see here is that there is this about 200 megahertz band available here on the lower 5 gigahertz band. So the same band, if they divide it into 20 megahertz channels, you get 8 different channels to operate on, right, in 20 megahertz. But then you can also divide that into 40 megahertz channels. In that case, you get 4 channels to work on, 8, 46, 54, and 62, right? You can further bond that, and if you bond that into 2, you get 42 and 58 channels at 80 megahertz. And finally, at 160 megahertz, you can get one single channel in the 200 megahertz band, which is at the 50 or the 42 are basically called, these are the center frequencies of that band. So all the numbers that you are seeing are basically center frequencies, and there is some mathematics involved into how this number gets converted into the corresponding band number. Anyway, just for your information, uh, basically the idea here is that in Wi-Fi you can actually bond these, basically aggregate the bandwidth. Now, why this is important? Many of you may not be aware of this. Like all of you, by default, when you configure any access point, you put the default setting is to put the Wi-Fi access point on 20 megahertz. But there are applications where you need bigger throughput. Let's say you're doing streaming or you need higher throughput, right? In that case, you can actually add up these, or you can set up a 40 megahertz channel, even put a 80 megahertz channel. Now, what are the disadvantages of doing that? The disadvantages are that all of a sudden, the number of channels that are available to you to design your network are reduced, right? As I said that this 20 megahertz channel. So if you are having one access point in 36, you can't have any other access point in 40, 44, 48, and 52. Directly, you can have if access another neighboring access point in 56 band, right? Because otherwise there will be channel interference. So as you increase the number of, as you increase the bandwidth of a channel, your number of channels to design your network reduces. So that's why you need to be cautious about how you aggregate it. Now, an example being that if you are having a dense network where there are several access points, then perhaps a channel bonding help you. But if you are having only a few access points and they are separated there's a separation between them. So it is possible that you can put them on higher frequency bands like 80 megahertz, 40 megahertz, or if you're supporting 160 megahertz as well. Okay. So if you need more bandwidth, you need to add, you can increase the band channel here. Okay. Channel width here. I hope everyone has understood this concept. Now, this is another interesting thing, but a lot of people get it wrong, as in difference between throughput and bandwidth. And they use it so interchangeably because people don't understand the difference between the two. And a lot of times there is also a big confusion when people talk about 300 megabits per second, 1200 megabits per second, and now 2.2 gbps, and all those speeds that people are talking about. And people make a lot of buying decisions based on the numbers that they see on the boxes, right? As in, oh, they're offering me 1750 megahertz or 2.2 gigahertz and so on. But people fail to understand some basics behind all of these. So first of all, let's understand there is a concept of what is called as a frequency bandwidth available for Wi-Fi. So frequency bandwidth is basically the frequency that is available. So if you create a 40 megahertz channel, you're getting 40 megahertz bandwidth there. Okay. So the higher, if you get a 40 megahertz channel, you are having more bandwidth. If you're having 80 megahertz channels, you are having more bandwidth than that frequency bandwidth. But there are other things that play an important role in your data rate. So there is the throughput is actually measured in data rates. So bandwidth means what is the channel bandwidth that is allocated to you, whereas throughput is what is the data rates that you get. Now the data rates are dependent on a lot of factors. So there is a concept of data encoding, modulation techniques, the contention in the channel, the encryption that you use on your Wi-Fi networks. All of these actually determine your data rates. And whatever advertised data rates that you see, so you get a 300 Mbps data rates. This is basically data rates combined. These are combined data rates on all the bands. So you're having multiple bands. Let's say you have a dual band or a tri-band radio or tri-band access point. So these are advertised data rates are basically the combined data rates on all the bands. Now, one of the most important thing which the almost all the Wi-Fi companies don't tell you when they advertise 300 Mbps or 1200 Mbps is that Wi-Fi is based on a protocol called CSMA-CA protocol. And those who are a little technical, there's a concept of what is called as a half duplex. Okay, so half duplex means when someone is talking, other one needs to hear. As in right now it's whatever conversation we are having is a half duplex because I'm talking and you all are listening. Now imagine what would be the scenario here when all of us are talking at the same time. There will be total chaos in this webinar, right? So same thing happens with Wi-Fi as well. Like Wi-Fi by definition or by design is a half duplex protocol. So it means that it is half duplex. Automatically, your bandwidth, whatever the frequency bandwidth that you're talking about, actually it's divided by 50% for older technologies. Older protocols, we are talking about people don't use it. A, B, G protocols that were used earlier. Now with 802.11n and AC, they have done some intelligent things in that and they have reused some of this. So in a sense, you get about 65 to 70% of the actual data rates when you have deployed it in an ideal scenario in your premises. So what is an ideal scenario? You have access point and your device is right next to it. That's the ideal scenario, and there is no other interference nearby, as in you are in middle of somewhere where there is no other Wi-Fi interference or any other radio interference. Okay, that's a kind of an ideal scenario or kind of in a lab scenario where you're talking about, right? So when you're talking about 300 Mbps of data rate for AC access point that you're using, you're getting into in the range of 60 to 70% of the data rates by default by the definition of how Wi-Fi works. And then there are many other factors that actually determine your data rates, including the distance between your device and the Wi-Fi access point, the environment around it, the noise in there, the co-channel interference, and many technical factors get into what are the actual data rates that you're going to get. So the other important factor that goes into what is the aggregate throughput. So whenever we are talking about Wi-Fi or Wi-Fi performance, what people talk about is aggregate throughput. What aggregate throughput means, what is the throughput or what are the data rates that a particular device, like let's say my laptop is currently connected to my Wi-Fi access point, what is the aggregate throughput my Wi-Fi access point is going to get, right? And because Wi-Fi is a shared medium, everything happens in the air, right? Wi-Fi signal goes through the air. So it is shared between all the devices that are connected to the Wi-Fi access point. And all of them would be trying to transmit and receive at the same time. So it is shared. So even if you are buying a 300 Mbps N series access point, and you're talking about 65 to 70% data rates that you get because Wi-Fi is by definition half duplex. After that, if there are multiple devices connecting to it, that means all of them are sharing or competing with for the data rates or for the bandwidth on that particular Wi-Fi access point. So automatically number of devices that connect to that Wi-Fi access point also determine your aggregate throughput that a particular device is going to get. So as you can see that Wi-Fi, when you talk about it, like marketing thing is different and the technical aspects of Wi-Fi are quite different. As in we are also a Wi-Fi company. We also sell access points. We also advertise our Wi-Fi access points to be 300 Mbps or 1200 Mbps or 2.2 Gbps and so on. But these are basically the theoretical speeds, and also these are actually what that bandwidth can support. But as soon as you put a Wi-Fi on top of it, these are the kind of realities that you will have to encounter. So now you guys have understood what is Wi-Fi and some of these basic concepts. Now let's look at different types of networks. And many of these are, as I said, this is very basics of networking, and some of you will really learn a lot about it, because I think this is something that you guys have studied perhaps in your engineering days and so on, but these nonetheless are quite important concepts when you build Wi-Fi networks and when you design or manage Wi-Fi networks. So I will quickly go through this. There are 3 or 4 different types of networks. Many of you know what is a WAN network. WAN network is basically wide area network, and there could be wired or wireless wide area network. This Then there are multiple different types of technologies which are used in wide area network. I'm not going to get into any details of this. The technologies like frame relay, ATM, MPLS, these are the kind of technologies that are used, or protocols that are used for a wide area network. In fact, the mobile network that we use today, like your 4G and so on, these are all they are all categorized as wide area network because they cover a large geographical area. So your CDMA, GPRS, 4G LTE, all are called wide area networks. Then there are something called metropolitan area networks. Metropolitan area networks, and W stands for wireless. So wireless metropolitan area networks. Okay. So they are designed for, like a WiMAX was a technology that was designed. It was designed for a metropolitan area network earlier. It didn't succeed because LTE took over and so on. But nonetheless, the metropolitan area networks, when Wi-Fi technology is used for metropolitan area networks these days, because and it's used effectively as a cellular offload. Um, then we have, after that, we have something called LAN networks, which we all are familiar with. Ethernet networks, which is the wired network that you have it in your offices, even sometimes in your homes, and wherever you go, as in all the places have Ethernet deployed, right? And now the Wi-Fi network, as in, which is called WLAN network. Okay, so wireless area network, it's called. It's also now becoming a de facto. It's kind of competing with Ethernet. To now almost everyone has wired area network in their premises, right? And then after that, there is something called personal area networks. These are wireless personal area networks. So then within the homes, people have now smaller networks, and there are a lot of protocols, a lot of research going on in personal area networks, where we are people talking about entertainment, or very small networks like your Zigbee and Bluetooth, which are basically the networks that you use in personal for personal reasons. So they are part of the personal area network. Okay, so let's get into some more Wi-Fi basics, as in this is going to be getting into a lot of nitty-gritties of what Wi-Fi is. So all of you may be knowing that there are 2 types of modes. One is called the ad hoc mode and the infrastructure mode when you set up Wi-Fi. The ad hoc mode is when there is no single gateway which is overseeing a particular Wi-Fi network. That means every Wi-Fi device can connect to any other Wi-Fi device. That is called the ad hoc network. So generally, ad hoc networks are not there or not widely used. But technically, if you have a laptop or your phone, can be configured in an ad hoc mode, and they can talk together. So basically, they don't need a central Wi-Fi access point or a Wi-Fi router in an ad hoc mode. So my laptop can, if it is configured in ad hoc mode, can talk to another neighboring laptop directly without an access point. But the prevalent mode everywhere is the infrastructure mode, which is where the access point or a Wi-Fi router is sitting in between, and everyone is connecting to the Wi-Fi router, and the communication is happening through the Wi-Fi router. Okay, I'm sure all of you are aware of what that means. Now, what I've shown on the right hand side are basically 2 ways in which these routers can be connected. The most easiest and the simplest method is putting Wi-Fi router on an Ethernet backbone, right? And that's what everyone is aware of, that your Wi-Fi router can connect to Ethernet, and it becomes a part of the Ethernet backbone. But the other way of doing that is also called as mesh. So your Wi-Fi access point, one of your access point is connected to the, and then it creates a wireless link, which is shown in the dark blue color. between two access points, and that is called meshing of two networks. So that's another way in which the Wi-Fi access points can be connected into a particular network. So again, now what is Wi-Fi access point? It's basically a Wi-Fi router that sits between the client stations, basically laptops and devices, and is responsible for switching data back and forth or connecting devices back and forth. It's like a switch for the wireless network. Essentially, it's a wireless switch in a sense. Obviously, it does a lot more than that, but in a very simplistic way, if you look at it, it is basically a switch. It also is a router because the access point is also connected into your Ethernet backbone. So it kind of bridges two different networks, your Ethernet network or your Wi-Fi network also. So it can function as a router as well. Please, Mike. Oh God.
Nice to meet you.
Then the basics of Wi-Fi, what is included in Wi-Fi? So there are access points, there are client stations, and then there is a distribution system, right? So the distribution system is what I just told you. It could be an Ethernet distribution system. That means the distribution system is used for connecting different devices or different access points or clients stations between each other. So that's a distribution system. And the distribution system can be based on 2.4 gigahertz or it can be based on 5 gigahertz. Now, a little more basics and understanding of these languages. I think many of you use these terms on a frequent basis like SSID, BSSID, and so on. So what are these things? As in, I'm trying to kind of out of these things. So on the right hand side, you'll see what is called as a basic service set. What is a basic service set? In order for you to, basic service set is basically a wireless network, a simple wireless network. But when you talk about a wireless network, there are multiple things. There is as we saw, that there is a distribution system, there is a access point, and there are client stations. All of them become a part, and all these things combined is called a basic service set. Okay. So basic service set is basically all these components, and then the basic service set area is basically the coverage area. That means the area that the Wi-Fi access point will cover is called the basic service set area. Now, each of these access point has a unique identifier called the MAC address or the MAC ID. Okay. So technically speaking, the way Wi-Fi protocol is designed, there needs to be at least one MAC ID for that service set, whatever service set you are creating. Okay. So that is the basic service set, and the MAC ID is associated. But it is technically possible to have multiple BSSIDs. That means you can have multiple IDs. Means usually MAC ID is used as an identifier, but you can technically use any. Means Wi-Fi protocol doesn't specify that it has to be AP MAC address. You can use anything as a BSSID as long as it's unique. So generally MAC addresses are unique, so that's why people use MAC address. But it is possible to have on the same network, you can have multiple BSSIDs as well. And there's a concept of dynamic rate switching. I will get into that later on in my presentation because that's a very important concept, and many people fail to understand it when they deploy or when they operate any Wi-Fi network. What is dynamic rate switching? Then there is a concept of extended service set. Now, what is extended service set? Earlier in the diagram on the top, you saw that there's only one access point and multiple client devices, right? But when you have multiple access points connected with each other through a distribution medium, that is called an extended service set. So here you can see the second diagram, you will see that there are two Wi-Fi access points connected through an Ethernet cable. And there are multiple, there's a client device which is going from one service set area into another service set area. And this concept of the client going from one coverage area, what is the service set area? Which is basically a coverage area. So one access point, when it moves from one coverage area into another coverage area, that concept is called Wi-Fi roaming. So you can see that client device as the person is walking down the hallway or within the premises, and he will be hopping from one AP to another, right? When he is going from one area into another, and that concept is called Wi-Fi roaming. Okay, and then have these multiple devices together, they create what is called as a mesh network. So that is another, I think we've already discussed it earlier. What is a mesh network? When you have all these Wi-Fi access points, instead of using the Ethernet as a distribution medium, if they use wireless as a distribution medium, you create a Wi-Fi mesh. Now, important question is, and having multiple SSIDs or BSSIDs, well, do they affect performance? Now, many people don't know this, as in when people call us and say, we have one access point which is having 16 SSIDs in it, and that's a superior access point, because people are always looking at numbers. The bigger the numbers, people feel that it's better. But actually, in fact, from technology perspective, having or broadcasting multiple SSIDs to one point is actually affects your Wi-Fi performance to a great extent. Now you may ask me why, as in why does the Wi-Fi access point if instead of having two SSID broadcasted, if I'm broadcasting 8 SSIDs, why does the performance of that Wi-Fi access point goes down? The simple reason is that the more number of SSIDs that you have, there is a more number of traffic or more processing and more frequency gets allocated to that. So please remember that a lot of technical things are happening behind the scenes when Wi-Fi is working. There's a concept of beacon packets. There is a lot of control frames, management frames that are going back and forth between your client devices and the Wi-Fi router when you are connected to Wi-Fi. And as you increase the number of SSIDs, these packets, these beacon packets, these control frames, they increase in that manner. As in, with one SSID, you will have less number of overhead within your Wi-Fi network. The more number of SSIDs you put in onto your Wi-Fi access point, the more the access point needs to allocate, or more computing it has to do, one, and more number of bandwidth gets utilized for the beacons and all the control frames that are exchanged between the devices and the access point. So uh, please get this in your mind, that just having a lot of SSIDs, like 16 SSIDs, or broadcasting so many SSIDs on your Wi-Fi access point doesn't always mean that your access point is superior, or you're going to get superior performance. In fact, the more number of SSIDs you broadcast, you are actually degrading the performance of your wireless networks there. Okay, now this is another interesting concept. People use it repeatedly, but a lot of people don't know much about it. As in, there are different modes on an access point, and access points can be configured to run in different modes. And these are 6 different modes that we have defined here. One is called a bridge mode. Then there is a repeated mode. There's an access point mode, a mesh mode, a sensor or a scanner mode, and a client mode. So I presume some of you may be already knowing this, but let me quickly explain what is a bridge mode. A bridge mode is basically your access point becomes like a switch, like your regular Ethernet switch. It just bridges an existing network. So it acts like a bridge. One of the important things that the bridge does, which your Ethernet router also does, is that it creates what is called a forwarding tables inside it. There's a lot of rules, and basically where the packets needs to be forwarded. There's a lot of optimization that the Ethernet switches these days do by caching things and so on. So a wireless bridge will do that. A repeater mode basically will repeat. Repeater mode is generally used for extending the signal. Like a lot of people know that in homes and all, people want to extend the signal, right? It just takes a signal and will just repeat the signal on the other side. So it is like a dumb repetition. So in case of bridge mode, it's actually bridging it. So there's a tables and all these things are maintained. In repeated mode, it's just broadcasting it in the other direction. Means repeating the signal in that. Then the most important mode that the access point works in is called the access point mode. AP mode. And this is the mode in which it is functioning as an access point, and it is also allowing the client devices to connect to the other side, right? Means basically it functions not just as a it does a bridging, but it also functions as a router, because on the other side, typically on an access point to a Ethernet circuit, or like a wired circuit, right, or wired connection, and that wired connection is generally connected to your internet, right, or internet or your local network and so on, right? So just a minute, people are drawing again. I've told people not to draw on the board. So an access point mode, when the client connects to the access point, it basically is also connecting to the wired network on the other side. So that's the access point mode. The mesh mode is when that access point all uses a part of its bands or part of its radio to connect to another access points wirelessly. So it's basically a wireless link that gets connected between the access point, or between the two access points. That's called the mesh mode. And then there is a sensor mode. This is a very unique mode in which it doesn't do any broadcasting of Wi-Fi signal. Actually, it actually just instead of broadcasting, it is only listening. It is just understanding what is going on the Wi-Fi signal. So that is called the sensor mode. And lastly, there is something called the client mode. Client mode is what your devices are connected. Your laptops and your phones are basically running in a client mode. That means they are not functioning as a um, router. So someone has raised an hand. Let me see what the question is. Um, yeah, please unmute yourself and ask a question. Someone had a question.
No, I will ask at the end of the session. Okay.
Okay, great. Okay, no problem. Thank you for understanding that. So yes, there is a client mode, and so client mode is where there is. So in a client mode, you will not have any forwarding tables or anything like that. It is just a simple Wi-Fi. Your device that works is a client mode. So in fact, this week we are having a discussion with one of our partners, and they were thinking that they could use one of the devices which is primarily designed as a client mode, like the Wi-Fi chip on it was designed as a client mode, and they wanted to convert it into an access point mode. But if you can realize that if there is no there isn't sufficient memory, or basically the software is not there to control set up the forwarding tables and so on, you can't run your access Wi-Fi, your technically your laptop into into an access point mode. You will have to provide all the necessary software to convert your laptop into an access point. That's when the drivers and all need to be enabled. Okay, this is little more technical. I won't go into the technical details, but just on a high level, I'm sure many of you know that Wi-Fi is made up of a lot of bits and bytes and packets and frames. For those who are technically oriented and knows in depth about computer networking, can know what are frames and packets and bits. But interesting thing that I'm going to talk about are these three frames, as in there's a concept of management frames, control frames, and data frames, and also a concept of beacons. Okay, because it's one of the important aspects of Wi-Fi or basics of Wi-Fi. Okay, so there are three types of frames that are basically used in Wi-Fi. Okay, when people are talking about throughput from Wi-Fi, they are mostly concerned of the data frames. Okay, because the management frames and the control frames are generally taken care by the Wi-Fi access point. The people who manufacture the access points are generally worried about how to optimize them and use them and so on, all the protocol implementation of it. But uh, the another important concept is called the beacon, and many of you have heard this. There's a Wi-Fi beacon, and is also called as BLE beacons. Beacon is basically a technology that, or a particular aspect of Wi-Fi, where every client device basically has to respond. A access point will send out a beacon to all the devices that are connected, and they have to respond back. And that is used primarily to sync the clock between the client device and the access point. the syncing of the clock is extremely important in Wi-Fi, because if you don't sync the clock, clock means there is actually a special clock, or basically a special timer, which is working in both the client and the access point, and that needs to be constantly kept in sync. And that is the role of a beacon. So every, I think the beacon frame is sent, like I think about 10 or 20 different 20 different beacons are sent to a client device every second. So that's how busy your client is when you're connected, as in there's a lot of things that is going on constantly from the access point to your device. And there's the concept of supported data rates and association and authentication. So what are supported data rates? So as you may know that all of you are concerned about 300 Mbps, right? Or 50 in the past when we are using the G series, we are 54 Mbps, 150 Mbps, now 1.2 Gbps and so on. So these are basically theoretical data rates, but there are the data rates when you move away from the access point, or there's interference in the access point, they don't automatically go from 54 Mbps to 48 Mbps or for 45 Mbps. I say it's not. It happens in a particular rates, as in depending upon, there's some mathematics involved there, that your the kind of speed, the dropping of your speed between the client and your router happens in kind of supported data rates. And you can read about it, as in it kind of drops in certain intervals, and that is called the supported data rate. Then let me see if there is a slide for authentication. Yeah, okay, there is one more slide here. So authentication and association, so these are two other important aspects of Wi-Fi. And then authentication means when you connect to a Wi-Fi, basically. So first of all, the control frames. So the management frame. The management frame is used to discover the access point. So where is the management frame? Because when you have a client, when the client decides to connect to a Wi-Fi network, it is using the management frames to discover the access points. Okay, and join the BSS. That means the basic service set. It wants to join that particular basic service set. The control frames are used to acknowledge the successful transmission and reserve the wireless medium. So once you're connected to the access point, and that means you're a part of that wireless network, then how you participate in that wireless network is controlled by the control frames. So there are a lot of protocols there, and there are a lot of acknowledgements and so on that happens. I will not get into the nitty-gritties of there. There's concept of request to send, clear to send, and all these other concepts are there. So these are all part of the control frames. And beyond that, once you have got the control, that means the control frames are basically used like when you are a part of a Wi-Fi network. When your device has the permission to transmit data on the Wi-Fi signal is controlled by the control frames. Now, once you have the access to transmit the data, then the data frames come into picture. They actually carry the payload or the actual data from your device. Okay, so the management frames are used to discover the APs and be a part of the network. The control frames are used that when you're a part of the network, they help you reserve the wireless medium for you to transmit and do a successful transmission, and then the data is used for actually transmitting the data. Now let's look at into a little bit more detail about what happens. So here, as I told you, these are the management frames. On the left hand side, these are different types of management frames that are there in the Wi-Fi signal. As you can see that there is a beacon that is sent, and actually something called a state machine that happens when a particular device connects to a Wi-Fi. So the Wi-Fi device, when it connects to the Wi-Fi radio, goes through different states: state 1, state 2, state 3, and state 4, and so on. And what happens in each of those states is highlighted on the right hand side. Okay, so first and foremost, the Wi-Fi access point, as I told you, will send a beacon. The beacon will tell the Wi-Fi access point that, okay, basically it will ask the device, before you start communicating with me, sync the clock in your device, because you may be coming up with a different clock, and if your clock is not in sync with mine, then there will be problems with us transmitting the signal. And then the device will send something called a probe request. So probe means the client will actually try to find out which is the best Wi-Fi access point that I need to connect to, because the Wi-Fi, there will be multiple access points nearby. So the probing is used by end device to find out the best access point it needs to connect to. So all the access point will give a probe response. Based on that probe response, the client will decide which is the best access point. So generally, the clients have some algorithms in it that based on the SNR values and the signal strength and so on, it will connect to the best access point. Okay. After that, the client initiates an authentication request. And this is not the authentication that you know of. Like when someone says authentication, that means you think about the network authentication of username and password. This is not. This is a lower level authentication that is happening. This is basically happening at the lower protocol levels. And if you get a successful authentication response, at that time it will do something called an association with the access point. Okay. And there are a lot of, if those who are interested can go into a technical detail, frames and all that are exchange, but essentially this is how the Wi-Fi device gets connected to an access point. Okay, now with that, as soon as you connect to an access point, obviously there is a concern of security, right? And this is one of the most important topics of Wi-Fi, because Wi-Fi is an open medium, because there is no security, there is no physical security available in Wi-Fi. Unlike Ethernet, like let's say you have an Ethernet switch and you have an Ethernet network, unless the person has access to physical access to your office, so he's inside your office, has a cable, and he has access to your switch, he won't be able to connect into an Ethernet medium. But in case of Wi-Fi, the person can be even standing outside your office, right? And because it's a radio waves, he can catch it. So that's why Wi-Fi security is extremely important for wireless Wi-Fi. And many of you are already aware of this. There are multiple security mechanisms. WEP, which is outdated now. Now WP8 was the another security, which is also outdated. WP8 personal, that was an older protocol. Now most of the companies or most of the people use WPA2, either a PSK, which stands for personal, or WPA2 enterprise, which is .1x authentication. So it's the first one, WPA2 personal, is usually used in your homes or in your small offices, where you use a simple password. Now, what are the disadvantage of a WPA2 PSK or enterprise? PSK can be actually hacked because it's using a fixed password, right? Even if you have created a very strong password, there is concepts of brute force systems, and a lot of hackers have a lot of sophisticated tools to actually can technically hack a Wi-Fi password. Okay. Whereas WPA2 enterprise is a next level of the Wi-Fi security, where the key basically is there's a encrypted, basically the encryption key, it keeps on rotating through a radius server, okay, using the WPA2 enterprise. So there is no fixed constant key. So even if someone hacks the one key, within some time the key is going to change. So that essentially is called WPA2 enterprise security. Someone keeps on drawing, so I get distracted with it. So then there is a concept of AAA, which is authentication, authorization, and accounting. This is not a topic of this discussion. We'll have another maybe webinar where we talk about BSS and what is the function and so on of it. And then there is a VLAN security, which is via virtual LAN. So you segregate the LAN and you segregate the networks into different parts, and then you enable VLAN security. So there are different types of securities on wireless networks. Okay, so let's get into a little bit of Wi-Fi architecture. Okay. Now, many of you have already known, earlier we talked about the management packets, control packets, and data packets, right? Similarly, at an architecture level, there are three types of planes, we call them. Okay, they are called management plane, control plane, and data plane. Okay, I'm sure some of you know these concepts because they are lot of companies like Ruckus, Aruba, Cisco, all these big companies, they actually discuss a lot about this. So let's understand these concepts very well. So whenever you are evaluating products, whenever you are looking at different vendors, these concepts will be very clear for you. So what is a management plane, or what is the function of a management plane? A management plane's function is basically management of the devices. So why do you need management of the devices? That's another interesting question. Like earlier, when people used to buy access points, they were generally fat access points and an open architecture. That means people had every access point had to be individually configured. That means you buy one access points. Like let's say you today you buy your home Soho router. You have to go in and log into it, uh, uh, and um, so the management plane does basically allows you to manage all the networks, all the access points through one controller. What I was talking about was the fat access point, right? The fat access point we used to individually manage those access points, but that soon realized that when you have to have manage hundreds of access points, it is very hard, as in you can't basically configure every access point individually. So that's when the concept of a controller came in, right? And then there are a lot of research happened over it, and a lot of new architectures have popped up. We'll discuss shortly. But before that, let's get into management plane, control plane, and data plane. So the management plane is the plane or functions that are responsible for the management, administration, and monitoring of the access point. So that is called the management plane. So whenever you buy an access point and you buy a controller with it, the controller offers you a management plane. You can configure the access point, you can monitor the health of the access point, you can monitor how many devices are there connected to it, what is the throughput of that access point, and lot of technical parameters, right? Which you might see in a lot of controllers today. And it also allows you to configure. You want to change the SSIDs, you want to change the channels, you want to change the transmit power, many other configurations you want to change, you want to enable VLANs on it. All those management and configuration functions are done by the controller. So essentially the controller provides you a management plane. Okay. So the management, I hope everyone is clear about the management plane. Now there is a concept of a control plane. The control plane is now the next level where two devices, when the access points are functioning within the Wi-Fi network, then there has to be some intelligence that needs to be created for doing things, for optimizing your network. And that is done by the control plane. So there is a signaling that happens between the access points. Like say when you're roaming, so the seamless roaming from one access point to another is done by the control plane. Similarly, when you're doing meshing, the meshing concept requires the control plane to work correctly. So there should be a control plane. So the signaling or the kind of intelligence that is there is part of that control plane. So control plane is essentially the intelligence and the features that are implemented between the access points, that the access points talk to each other. And sometimes the access point need the help of the controller to do that. But the controller acts as a mediator or a facilitator in this case. The control plane is responsible because a lot of intelligence is gathered by the access points, and then a decision is made. So example being, let's say, you know that there is some concept of dynamically changing the transmit power of an access point. So how do you determine how you want to dynamically change the transmit power? The access point needs to know what are the neighboring access points and whether there is a lot of interference between those devices. When it learns that, it automatically starts changing its own settings. So that is all these things or bands and all these concepts, they are part of the control plane. And the data plane, which is called the user plane, essentially is used for transmitting of data from that, and how the data gets transmitted outside is part of the data plane. Okay, now everyone, I think I've explained about the fat access point where everything is configured within the access point. But then there is the concept of a central architecture. The central architecture means you have a central controller which is managing all these access points. So this is kind of a de facto standard now, that you buy a Cisco WLC, you buy our Unibox controller, you buy any other third party controller. The controller is responsible for managing, controlling the access point, and that is called the centralized architecture. And then there is a third type of architecture which is called the distributed architecture, where one of the access point functions as a controller. I think many of you know about Aruba. Aruba has kind of pioneered that this kind of architecture, and some others have actually kind of mimicked that. So in that, this is a distributed architecture. So there may be a controller in there also, but the controller kind of delegates some of the functionality of the controller to one of the access points on the network. So it kind of becomes a combination of it. Okay. I hope things are clear here in terms of how different architectures are laid out for the access point. So yeah, these are two different types of diagrams. I think I've clarified it. So the central architecture, all the management traffic of the access point is sent over to the WLAN controller, which is inside your data center or inside your server room, right? And it takes a lot of decisions. In case of distributed architecture, there is still a NMS or some kind of a server controller is there, but a lot of decision happening is taking place between the access points. So the data and control functions are distributed amongst the access point, which is and it is facilitated by inter-AP communication. So that is the distributed architecture. Now let's understand what is the concept of a wireless controller, or what are some of the functions of a wireless controller. Many people know about a wireless controller, but there's a lot of confusion about that. So wireless controller, on the left hand side, we have listed out all the functions that a wireless controller is supposed to be doing. So one is the SSID management. So you should have multiple SSIDs. They should be configured in the access points and all the settings of those SSIDs. You should do VLAN management. It should implement layer 2 security. The WPA2 security, all those settings has to be done by that. It should provide you captive portal. If it should provide you something called WIDS, which is intrusion detection system. It should do dynamic RF management. If QoS management of the bandwidth and QoS management, and also does some firewall functions, right? Basic firewall functions. So these are essentially what people do in case of, and you can create profiles, WLAN profiles, and so on. So these are basic functions of any wireless access point, wireless controller. Okay. So the next thing we are going to discuss about are what are different LAN developments, deployments. So I'm sure all of you are aware of it. There is indoor, outdoor, and then there are Wi-Fi hotspots, which are basically used in public venues. So indoor are further divided into SOHO networks, enterprise network, and branch offices. Okay. So networks are basically small networks, like 1 or 2 access points, generally deployed in homes or small offices, where you don't really require a lot of management. Even a fat access point is enough for a SOHO network. And generally that's what people do. They generally have a fat access point deployed in a SOHO network. But enterprise networks and the branch networks, where things get complicated, because in that case, your access points there are multiple access points. There are a lot more security standards, policies, and so on, where you require controllers, you require both the control plane, management plane. All these things are become relevant in case of enterprise and branch offices. And many of you have a part of maybe doing ISPs also. So ISPs use Wi-Fi technology for last mile connectivity, or for point-to-point connectivity, or point-to-multi-point connectivity. So Wi-Fi, when it is deployed in point-to-point and multi-point connectivity, that is a very different discussion there, because the design scenarios there are quite different. So we'll get maybe this presentation may not be able to cover that, but that's where Wi-Fi is used. And finally, there is something called public Wi-Fi, which many of you are aware of. When the Wi-Fi is deployed in a public environment for the general public, that is called a Wi-Fi hotspot. Now, this brings us to another very interesting concepts of what is called, what I call as design concept, wireless LAN design concepts. And I think this will be very, very interesting for many of you because there's a lot of misconceptions that we find with our many people about how Wi-Fi operates and how to make the right Wi-Fi decisions here. So I'm categorizing these design concepts into 6 different categories. One is the coverage. So what are the things that you need to look out when you're doing a coverage design of your Wi-Fi network? What are the things that you need to consider when you're doing roaming decisions, or you want to have roaming, seamless roaming on your Wi-Fi network? Then channel design, like how do you design the channel so that there is very little co-channel interference between the access points? Then the capacity design, like when you're having a very dense venues, or how do you handle the capacity of your Wi-Fi network? Antenna design. So if you're doing an outdoor deployment or even in an indoor deployment, how the antenna design affects your performance of your Wi-Fi network. And then the physical environment, as in how the physical environment plays an important role in your Wi-Fi design. So if you understand some of these concepts, you will be able to really build a very good wireless network, as in because these concepts play a very important role. Understanding concepts is very important when you design any wireless network. So let's go into them one by one. So coverage. So on the left hand side, the text basically tells you what are the different things that you need to be worried about when you are doing coverage design. And this is very, very important because almost everyone is concerned about coverage. Everyone is trying to optimize how what are number of access points that needs to be deployed. The lesser, the better, because it saves cost, correct? So let's look at these concepts one by one. So first and the foremost, many of you also do site surveys, right? And when you're doing site surveys, what are the things that you need to look for? So first is received signal. So what is received signal? As in, when you're doing a site survey at a particular location, or when you're doing a coverage design, you have to look at the received signal at different regions or within that premises. So if you're doing a site survey, the received signal is very, very important. And on the right, I've shown it a table about what is considered to be a good signal and what is considered to be a bad signal. Okay, so you can see that right from minus 30 dBm all the way to minus 95 dBm, the signal strengths are categorized. So anything which is up to minus 70 dBm is considered to be a strong signal. Okay, so if you are doing a site survey and you are having your tools, even if you are having a simple Wi-Fi analyzer on your laptop or on your computer, on your mobile, you have to look at these parameters. So people ask us many times what is considered to be a good signal. So a general rule of thumb, again, someone has unmuted. So any signal which is uh, 70 dBm. So remember, these are negative numbers. So basically minus 60, minus 50 are higher than minus 70 in this case. So anything which is higher than minus 70 is considered to be a good signal. Anything which is minus 90 dBm is a weak signal. And basically minus 95 dBm is considered to be a noise floor. The diagram below, I've shown you noise floor. Noise means you will not be able to determine anything on that when you are in that signal. Okay, so if you are getting minus 90 dBm or when you're troubleshooting your network or your clients and you're finding minus 90 dBm, then you know that the signal is weak. The next thing you need to be worried about is called signal to noise ratio. So even if you are having a very good signal, let's say even if you're having a minus 70 dBm signal, but your signal to noise ratio is less, then even if you're having a good signal, it doesn't help you within your design. That's why the noise, whatever we are shown here, minus 95 is an average. But if you are having a very noisy RF environment, that means there are too many Wi-Fi channels or Wi-Fi devices operating there. There are other radio interferences and many other things affect the Wi-Fi's Wi-Fi signals. So if you are having high noise, then you should be worried about the signal to noise ratio. So generally a signal to noise ratio greater than 25 is considered to be good, and anything below 10 to 12 is considered to be bad. So you have to pay that attention. So it doesn't, so please understand that just because you are getting a very good signal doesn't essentially translate to having a good Wi-Fi. Your noise is equally playing an important role. What is the noise in area for you to find out? So that's why people also look at noise to signal ratio when they determine how good is your Wi-Fi. Then the dynamic switching rate. I think I told you earlier I was going to discuss about this, what is called as the dynamic switching rate. So below you will see the different ovals that have been drawn here. So as I told you earlier, that Wi-Fi signal automatically starts degrading as you move away from the access point. And the degradation happens in kind of stages. It is not like a linear degradation. So let's take an example of a Wi-Fi access point, and you are very near to that Wi-Fi access point. Let's say you are within the 10 feet area of that Wi-Fi access point. At that time, unless there are no other factors in, you are transmitting at the highest rate possible. That is 54 Mbps in this case. They took an example of older Wi-Fi technology, but you get the point here. It's same thing is applicable for other devices as well, as in other newer technologies as well. So but as soon as you move away from this zone, your signal doesn't drop to let's say 52, 53, 54. It actually drops down to 36 Mbps, and then it drops down to 18 Mbps, and then it drops down to 6 Mbps. Okay, and then further it may drop down to 1 Mbps, and then even further as you go away. Now there is also very interesting concept which many of you are not aware of, and this is what I believe impacts a lot of things when you design your Wi-Fi network. That if you are having your devices in this particular range, let's say 6 Mbps, okay, then it adversely affects the people who are closer to that Wi-Fi access point, because Wi-Fi medium actually there is very interesting concepts. I'll explain it to you in a later slide, that it actually slows down the performance of your faster devices. So these speeds are not just determined by the distance also. These are also determined by the devices that you are using and the quality of the devices that are there as well. But overall it is divided, is controlled by the distance. Now, many times we get customers who ask us, hey, I want a Wi-Fi access point that will cover 100 meters radius. Now they need to understand that when they are asking for this large area coverage, and they are trying to build a good quality Wi-Fi network, these are kind of counterintuitive to each other. Because what is happening is that even if you are having a powerful Wi-Fi access point which is broadcasting to a large degree, if the devices at further away are connecting to this Wi-Fi access point, they are going to drastically bring down the performance of that Wi-Fi access point for the devices which are connected near to that access point. So just having a powerful access point, a powerful antenna or coverage is not always going to be helpful, is something that I wanted to make a point here. And people need to understand, means that doesn't mean that that's why a powerful access point is not good, but you have to understand your application properly, as in really is it needed or not, as in what is the real application that you're looking at. And just don't go with the assumption that if you are having a powerful access point, jiska range acha hai, means which has a bigger good range, doesn't mean that it is actually having a it's a good quality network. Okay, so the transmit power plays a very important role in how your Wi-Fi or your coverage is designed, or your Wi-Fi is designed. Okay, so that let's go to the next aspects, roaming. So what we have drawn here, there are three aspects that you need to look at when you're roaming. One is called the primary and the secondary coverage. So when you draw a Wi-Fi, you set up an access point and you draw a circle around it, right? That's how you think that the Wi-Fi signal is going to propagate. But that's not true. Actually, the reality is that when you are in an indoor environment or any environment, there are a lot of obstructions in between. There are a lot of the Wi-Fi signal is not going to be circular like this for an omnidirectional antenna. It is going to be something on like this. This is the real Wi-Fi coverage. Now here, this has to be taken into account. You need to understand this. And then the primary coverage area for any access point is the let's say you're talking about a access point A and B, right? So roaming is basically moving from one access point to another. So in this case, it is important that when the light gray area on the left hand side is the primary coverage area of the access point A, and the darker area is the secondary coverage area, because there a device is going to get a coverage from the neighboring access point as well. So this overlapping has to be taken into consideration. If two signals don't overlap, okay, and two real coverage signals, not like this theoretical, the real signals coverage don't overlap, then the user is going to get dropped off from one access point and then has to reconnect to the other access point. It will not be seamless. Then there is a concept of fast roaming. Basically, fast roaming is required when you are talking about latency. Let's say you are having a VoIP call, you're having a Skype call, and you're roaming from one access point to another. So what happens in reality in this case is that you are disconnecting from one access point and you are reconnecting to another access point. And that connection and disconnection actually takes several milliseconds. As in, I'll give an example. Generally, the connection from one access point to another access point takes anywhere up to 700 milliseconds. But certain VoIP applications, they require a latency of less than 150 milliseconds. What will happen in this case if this switchover, if it is taking 700 milliseconds for the reassociation to happen, then during that time period of 0.5 seconds, user is going to experience that disconnection. That means he's going to get a blip in his signal, as in he may lose certain words within that time. Like you'll see that clearly that things have happened, and that you will experience even for cellular coverage, as in you calls drop, or all of a sudden your voice goes away when you hop from one cellular coverage to another. So in an enterprise environment, this fast roaming is extremely important, and that is done by several techniques which are beyond the scope, and these are quite proprietary also. For every vendor has their own proprietary methods of doing that, but there is also an industry standard called 802.11r which is set up for fast roaming. So almost all the vendors start supporting fast roaming. And then the concept of layer 3 roaming, that means whatever we are talking about is happening at the Wi-Fi layer. Then there is also a roaming that needs to happen at the layer 3 also. So this is the another important concept that you need to be worried about. Then channel design. How will you design your channels? So you have to understand that the co-channel interference is one, and the adjacent channel interference is another. So what is adjacent channel? I think we discussed earlier in our presentation that the channel will overlap, the different channels overlap. So that adjacent channel interference needs to be taken into account when you design your network. Then how do you reuse your 2.4 gigahertz channel? What is channel reuse? That means the diagram below, where it is showing like a honeycomb, that is basically how you need to design your 2.4 gigahertz network, so that there is very little interference between different things. So you can see that the channel 6 is completely isolated when you're designing it in a there is no overlap between of any channel. So this is how you need to build your network when you are building a 2.4 gigahertz network. And then similarly on the 5 gigahertz channel reuse, you need to have ensure that there is maximum like separation between the if the channel getting reused. So here channel 149 is getting reused on another access point, but you can see that there are many other channels which are put in between. So the 60, 52, 36 and 64, they are sitting in between those two channels so that there is no channel interference that happens. Okay. And dynamic frequency selection. This is another important aspect for many access point, that if tomorrow you design this network and all of a sudden after you have designed, a new access point comes up here and it starts broadcasting in channel 1, which is interfering with you, then how will you dynamically change the channel? So that is called the dynamic frequency selection. So that means that you should learn what is going on real time in your area and dynamically change the frequency of your access point. Then whenever you require more throughput, you should go with 40 megahertz design. So again, as I told you earlier in my presentation, that 40 megahertz is available to you for when you are using a dual band access point, but you need to design or understand what applications you want, because the number of channels available to you in 40 megahertz will reduce. So there will be a lot of interference that will get introduced when you start using 40 megahertz channel. So unless and until you can design your network correctly, that's when you if you design your network correctly, then only choose the 40 megahertz design. Otherwise you can stay with 5 gigahertz channel. You can easily design using the honeycomb on the left hand side, and with this kind of channel structure, and adapt to RF power. So as I told you, that not all the time you need to be transmitting on very high, as in as you can see that if you 161, or let's say channel 6 is transmitting at a very high power, it is going to extend the signal beyond the channel 11 into channel 6, and is going to create interference there. So you need to make sure that you broadcast within that segment and there is little overlap between the same channels. So you need to make sure your RF power is adjusted properly.
Sir, is it possible to have that concept by itself?
Yes, yes. A lot of adaptive power means the power automatically gets adjusted based on the channels that are selected. Okay, so these are see, that differentiates your regular access points. That means this is what differentiates expensive access points from your cheaper access points. So
no need to do that concept, no, like manually changing the channels. So,
yes, yes. So you're right. Yeah, you're right. So that's when these things come into play, as in the expensive access points actually provide all this functionality to you.
Okay, thank you.
Okay. Okay, so the capacity design.
Can I just explain once again about the channel reuse thing? I could not understand.
Channel reuse?
Yeah, 2.4 gigahertz channel reuse. Can you just elaborate that? I couldn't get this.
Okay. Can others please mute? There is a background noise, please. So yes, to explain channel to 2.4 gigahertz channel reuse, see this thing on the right hand side. So what is channel reuse? Means, see, technically speaking, when you are deploying a Wi-Fi network, and let's say you had unlimited channels, so you will never put your access point on the same channel. If you had unlimited channels available to you, then what you would do is every access point will have a unique channel. Correct? So let's say you have unlimited channels to be used. So unlimited frequencies available to you, right? And you want to set up a Wi-Fi network. So you will put one channel on one. The second one, you put a 25 megahertz channel difference, and you put in the neighboring access point there, and you can keep on adding, because there is no restriction on how many channels are available to you. But because there are limited number of channels, that means there are only 11 channels, and out of which only 3 are really usable, you need to reuse the channels. That means the channel number 1 has to be in a network like this. So each hexagon here is basically a cell within a Wi-Fi network. So let's assume that we are deploying a Wi-Fi network in open area, completely open area, like a big open area. Okay. And there we want to design a network, correct? Now in this scenario, unless and until you reuse the channel, right? If you had unlimited channel, you will just keep on adding new, you'll keep on using new channels for every access point. But since you don't have unlimited channels, what you need to do is you have to reuse the channel 1 across multiple access points. Similarly, channel 6 has to be reused across multiple access points, and channel 11 needs to be reused across multiple access points. Then how will you design your network so that there is no channel interference between these neighboring cells? And that is called the 2.4 gigahertz channel reuse. So the diagram left is an ideal diagram of how you need to lay out your channel, your Wi-Fi network to reuse the channel 2.4 gigahertz channel. And the hexagonal diagram on the left hand side essentially is showing how to reuse the 5 gigahertz channels. What is the ideal assignment of channels in a neighboring access point so that there will be very little channel interference? I hope I've answered the question.
Yes, please. Thank you. But in a typical scenario, in a complex environment where we have controller-based deployments, the algorithm in that automatically takes care of this particular thing, right? We need not
to the best of its ability. Please remember that there are, in an office environment, there are a lot there are a lot of other neighboring access points, right? Your neighboring offices have it. So yes, you are right. In a controller based network, controller takes a lot of these decisions and in fact dynamically changes these channels. So even if you have changed, so a lot of times when you set up a access point these days, almost all the enterprise companies, enterprise Wi-Fi companies, they will ask you to select an auto channel. The reason they ask you to select an auto channel because their algorithms will basically select the channels for you rather than you designing it. But as an RF engineer or as a Wi-Fi engineer, you need to understand the concepts behind this. As in today, that's what, like, a lot of people use all these tools within the controllers, but the underlying theory is important for all of you to understand why it is done that way.
Thank you.
Yeah, capacity design. So we are, I think, last 2-3 slides are remaining. So high density environments. So when you're talking about high density environments like a conference areas or stadiums and so on, the diagram on the right hand side actually tells you what are the kind of requirements, required throughputs for different things. Like email web browsing, you require about 500 kilobits to 1 Mbps. If you're doing video streaming as like standard definition, about 1 to 1.5 Mbps, high definition 2 to 2.5 Mbps. So whenever you are designing any high density networks, remember earlier I told you about how much is the realistic speed that is available to you. And there are a lot of factors that go in there, as in there is multipath interference, there is absorption of your RF. Our previous video actually discussed all those things about RF, right? So after all of that stuff, you have to do the capacity planning by basically understanding what kind of applications are being used. What is like if people are going to do video streaming, like in a stadium, for example, so you need to better numbers into consideration and then do the density planning according to that. And so you need to have maybe a 4x4 radio, you need to have a tri-band radio, you need to basically design the access point. Like you can't put one access point and take 100 people there and ask them to connect. That's another interesting thing that people come to us. Oh, there are access points out there which supports 500 devices concurrently on our on that, right? There are a lot of things people are advertising, but my suggestion to all of you is actually do the math there. If you do the math, these are all theoretical speeds and these are without doing anything. They may be just connected to the access point, but in reality, no access point out there can support 500 devices when they are in the normal working mode. As in, it's very unlikely that an access point will be able to. There is not enough RF spectrum available.
Electric wire
the spectrum available for providing that kind of throughput through an access point. So when you do all those calculations, you will realize that it's the 500 and really some 256 devices on a 2x2 dual band access point are all basically marketing gimmicks. These really don't work in the real world. There's a concept of band steering. So many of you know what is band steering. I think band steering means, as you know, that 5 gigahertz band has much more throughput bandwidth available. So whenever a end device supports a 5 gigahertz radio, we should not allow that particular device to connect on 2.4 gigahertz. So leave the actually steer the devices to 5 gigahertz, and that is called band steering. And that is done by doing the following things. As you know, that there's a probe request that goes in. Earlier I in my discussion, but the access point is intelligent. It knows that it gets a probe request from 2.4 and 5 gigahertz both bands, so it will only respond to 5 gigahertz probe and not respond to 2.4 gigahertz. And so that the client will think that there is no 2.4 gigahertz radio here, and it will connect on 5 gigahertz radio. That is called band steering. And then load balancing. So this is a classic example of load balancing on the right hand side. So you can see that there are 4 access points. Let's say this is a large office space, and people are connected to that, right? This is very common in work environments, that most of the people get latched onto one access point. So after load balancing, this is what should happen, as in the devices will get equally distributed across access points. So this is another enterprise class, enterprise feature that is there. And last is called airtime fairness. Now this is also an important aspect, airtime fairness. So what is airtime fairness? And that's where having a very powerful Wi-Fi transmitter is not helpful. So as I told you earlier, that if you have a very powerful access point and you have like bunch of people who are connected, bunch of devices which are connected near to the access point, they are within the 15 feet radius of that access point, and then there are many other devices which are at the distance of 30 feet, 45 feet, 60 feet, and so on, right? Now what is going to happen is that when the Wi-Fi, basically, as I told you, there's a different kind of modulation technique. So it provides a that is open to that particular client to transmit the data. So what happens is it's kind of a multiplexing that is happening. So that means it allows clients to connect to the network and allows the client to transmit the data. Now, when the client is too far away from that access point, remember I told you that it degrades the data rates. It goes to even 1 Mbps. So it means that if the client is transmitting 100, let's say 1000 bytes at 1 Mbps speed, so if the device is further away from that access point, it is going to take longer time to transmit that. Right? Oh God, let me just, okay. So that is going to take a longer time. So by that time, the devices which are nearby are basically starved of bandwidth. Basically, at one point of time, the way the algorithm works is that once the wireless medium is available, it is only for few microseconds that it makes the medium available to a particular client, and the client needs to transmit. But once the client gets a control of it, it will keep on transmitting until it completes the transmission. So what it essentially means is that the devices which are near to that access point will be starved of the connection to that, or the bandwidth, when there are too many devices which are connected further away from the access point. So having a powerful access point really doesn't help when you are having when your application needs higher throughput. And that is what many people fail to understand. We try to explain it to them, but they fail to understand. I think many people just make their purchase decisions based on the range of the Wi-Fi signal, but it is actually a lot of technical things are in that. Even if the Wi-Fi access point has a bigger range, that doesn't mean that you will get a better throughput through that access point when you are at a further distance. And that happens to all the devices which are connected to it. This is another misnomer, as in more number of access point. What happens? So you can see the 2.4 gigahertz actually has a better penetration power than the 5 gigahertz. Okay, that's the physics behind it. Basically, the 2.4 gigahertz is a lower band, so it has more penetration power. So there are less number of 2.4 gigahertz radios that are required. So if you, for example, in an environment like this, if you install a dual band access point, your 2.4 gigahertz is going to create a lot of interference for the neighboring devices, because its throughput is higher. So either you need to reduce the transmit power on 2.4 band to make sure that there is little interference. Okay, so you can see this is basically rooms here, whatever you're showing in, and every access point is within every room. Now, in this case, what is going to happen here is that if your 2.4 is also transmitting at maximum power, it is going to create a big it will create a big muddle, essentially, like a RF interference will happen everywhere. So that's when you need to basically reduce the transmit power of the 2.4 gigahertz, or you need to reduce, you can even shut off some of the 2.4 gigahertz channels when you are designing your networks. So you have to look into these aspects when you design your RF networks. Then other physical environment, how the physical environment plays a role. So the physical, as you can see, that different mediums will have different mechanisms here. So you can see that concrete will absorb to a 12 dB of signal. The brick will absorb 10 dB of signal, whereas the drywall will absorb only 3 dB of signal. So you need to understand these environments. I think I've discussed it in my previous webinar, how the different materials absorb the signals differently. The thing that I wanted to talk to you about was this thing. Many people deploy actually Wi-Fi radios in hallways, or in the corridors, in hotels or in hospitals and so on. But according to RF experts, that's not a good design, and you can see the reason why. Most of the Wi-Fi signal gets propagated in this direction. This is how it gets propagated. So by doing this, what you do is, in order to penetrate your walls. Oh God. In order to penetrate your walls, you increase the power of this Wi-Fi radio. And by doing that, you are basically broadcasting that Wi-Fi signal across a longer distance, and it interferes. So if there is another access point operating on channel 1, it creates a lot of interference in between somewhere here. And that is bad. So you need to be very vigilant about how transmit power you're using on your Wi-Fi radio, so that it doesn't create a channel interference. Wi-Fi surveys, I think I've covered a lot of the topics here, but you need to understand first your customer requirements. You need to do capacity coverage planning. Security risk has to be considered. Their existing Wi-Fi network needs to be taken into account. And lastly, different. So these are some of the survey tools. I think we have almost 2 hours has gone. So we'll wrap up the presentation now. So this is, and lastly, there are Wi-Fi attacks. I will not cover them, perhaps in another this thing. So that brings me to the end of the presentation. I will open up this thing for any questions. Please feel free to unmute yourself and ask any questions if you have any. Otherwise, I will try to go through the chat windows.
Can you just show once again those tools that the previous slide?
Yes, these are the survey tools that are being used for surveys. Please, you can note them down. These are quite air magnet, Ikahu, and acrylic are very popular.
1 minute.
Okay, any other question? Oh, show the last side of Wi-Fi attacks. Okay. So again, this will take me long time to explain this.